Hello and welcome. My name is Lyle Tavernier and I'm speaking to you from NASA's Jet Propulsion Laboratory here in Pasadena, California. Today we're going to be talking about states of matter, and what I would like you to do first is to take a look at an image that I'm going to show you. In this image all states of matter are present, and what I'd like you to do is talk amongst yourselves and determine what states of matter are there and give an example of each state of matter that is shown in the image. All right, now that you've had a chance to take a look at that image, you might have said the ocean represents a liquid. You might have said the pier represents a solid. You might have said the atmosphere, even though you can't really see it in this image, except for the blue sky, of course, are the gases oxygen and nitrogen. And somebody might have even mentioned something about the sun. Now, the sun is made of hydrogen, and mostly when we think of hydrogen, we think of a gas, but the sun happens to be a special case where the hydrogen is in a state of matter called plasma, and we'll talk a little bit about that as we move forward. Before we can talk too much further in depth about states of matter, we need to answer this question. What is matter? So I'm going to give you a moment to think about that. All right, to be considered matter, something must have two properties. Matter is anything that has mass and volume. So when we talk about matter, we're essentially talking about the stuff around us. Now, it's important to understand mass and volume as well, so we'll talk about that. Mass is simply a measurement of the amount of matter in an object. For example, I have a small battery here, and if I were to measure this battery on a scale, I could measure its mass. If I took a larger rock, put it on a scale, I would be able to measure its mass. And if I put myself on a scale, I would measure myself, and I would find out that I have even more mass than either of these objects. Now, I mentioned scale, but it's important to remember that mass and weight are not exactly the same thing. When we talk about mass, we're talking about how much stuff an object has. If we take this rock out into space, it's not going to weigh anything, but it will still have mass. Weight is just the effect of gravity on an object. So that battery, myself, this rock, when we take ourselves out into space, we still have mass because it's simply measuring how much matter or stuff is contained within that particular object. Now, volume, on the other hand, volume is not what you're thinking if you're thinking about how loud something is. When we talk about volume in terms of states of matter, we're talking about a measurement of the amount of space that an object takes up. So I have a shape right here, a sphere, a baseball, and it takes up a certain amount of space. I could measure it, I could calculate the amount of space that this baseball takes up. I also have another sphere, basketball, and this basketball happens to be a larger sphere, so I can say that the baseball has less volume and the basketball has a greater volume. Now, when we talk about these two properties in relation to each other, if we compare mass and volume, we get something called density. And again, that's just comparing mass and volume. So think about the bowling ball that you see there, and think about a balloon blown up to approximately the same size as that bowling ball. And we can say that they have the same volume, but they definitely do not have the same mass. Inside that same volume, that bowling ball has much greater mass compared to that balloon, which has a lower mass inside that same volume. Another way you can think about that is, again, with this baseball. If you've ever held a baseball, you know it weighs around a pound. And if you've ever held foam, you know that it's pretty light. There's not a whole lot of mass in this ball of foam. However, they take up the same amount of space, so I could say that in the same volume, this baseball has more mass, therefore it has greater density. This foam ball has a lower density. All right, so keep those things in mind as we move forward and talk about these different states of matter. So the first one we're going to talk about is a solid. And to be considered a solid, an object needs to have two properties. Number one, it needs to hold its shape. So let's take this baseball again as an example. The shape is a sphere. I can toss it into the air, the shape isn't going to change. I can bounce it off the ground, the shape has not changed. Same goes for this rock. This rock is a irregular shape, But no matter what happens, I put it down, I toss it in the air, whatever I do with it, it's not going to change its shape because it is a solid, it has that property. The other property that solids have is that they have a definite volume. So what does that mean? Well, again, going back to the baseball and rock example, this baseball is not going to expand and take up more space. It's not going to shrink down or contract and take up less space. It's going to keep its volume. Same thing for this rock. It's not going to suddenly get bigger. It's not going to shrink down and become much smaller. Now, the reason that solids have these properties has to do with the molecules, the very small particles that make up these objects. Those molecules, they're tightly packed together and they vibrate in position. So what does that mean? Well, let's take a close look at ice. If we were to look at this piece of ice here, we can see that it has a solid state of matter. We can see it's holding its volume and its shape. It has a low temperature. And if we could look at the molecules that make up this object, we would see that they are indeed packed very, very closely together and they're vibrating in position. That vibration is simply because they've got some energy. Now, when we take a look here, you can see ice is a great example of a solid. It's the solid form of water. We have Mars and the planet Mercury, also here because they are considered solid rocky planets. So what I want you to do is take a moment and think about some different solids that you know of. Think about solids in the classroom, think about solids outside of the classroom, think about solids that are made by humans, think about solids that are not made by humans, and I'll give you a moment to do that. Okay, you've had a moment to think about some different types of solid examples. I'm going to give you an example of a solid that we use here at NASA. This is called solid rocket fuel. And just like other solids, it keeps its shape and it keeps its volume. In fact, in the inside of this rocket, you can see this solid rocket fuel has a pretty unique shape. That star-shaped pattern that we have in there is used to control the speed as the rocket lifts off. Solid rocket fuel is pretty interesting. It's powdered aluminum, similar to the aluminum you might find in your kitchen in aluminum foil, mixed with oxygen and a chemical called ammonium perchlorate. When it's all cured and bound together, it actually feels somewhat like a rubber eraser. All right, before we move on to talk about our next state of matter, I want to talk about temperature. Think about what temperature means to you. Usually when we think about temperature, we're thinking about how hot something is or how cold something is, and when we measure it, we say that something that is hot has a high temperature, something that is cold has a low temperature. But what are we actually measuring? Well, when we measure temperature, we are measuring a property that describes the amount of energy of those molecules that we saw. So the more energy that something has, the higher temperature it is. The lower energy it has, the lower the temperature. And I want to give you an example of something right here. I have two glasses of water here. One glass is hot and one glass is cold. I'm not going to tell you which one it is, but I want you to, as a class, figure out which one you think is hot and which one you think is cold. You don't all have to agree, but take a moment to look at those and figure out which one is hot and which one is cold. All right, you've had a chance to talk about which glass you thought was hot and which glass you thought was cold. Now we're going to figure it out, not by sticking a thermometer in there, but we are actually going to look at it through a special camera called an infrared camera. Now this camera will look at energy on the infrared wavelengths of the electromagnetic spectrum. And the infrared happens to be great at showing energy. So what I'm going to do is show you the 2 cups of water, and you'll see they look very, very different. The brighter colors are much hotter because they've got more energy. The darker colors are much colder because they have a lower temperature. So here you can see, looking through infrared, the glass on the left is hot, the glass on the right is cold. Even within the hot glass on the left, you can see there are some brighter and darker areas, meaning some molecules of water within that glass are hotter or have more energy than some of the other molecules in that glass. Now that we've talked about temperature and energy, keep in mind if I say something like adding energy to something, that's the same thing as saying making it warmer. If I say we're taking energy away, that's the same thing as making something cooler. So think about that ice cube that we had earlier And I would like to find out what happens when you add energy to ice. So somebody tell me what happens to a solid when you add energy to it, and what do we call that process? When we add energy to a solid, it becomes a liquid, and we call that process melting. And it melts and becomes a liquid. So let's add some energy to our solid. And you can see that when we do that, our temperature increases, our state of matter changes to a liquid, and now our molecules, because they have more energy, are moving around much more freely. Property number one is that they will take the shape of their container. So what does that mean? Here you can see water. I've added red food coloring to make it a little bit easier to see, in a cup. And because it's in a round cup, it has a cylindrical shape. I can't really turn it too far to the side because otherwise it would spill everywhere. But if I were to take this water and pour it into a rectangular prism, that liquid has now taken a new shape. And again, I can't tilt it too far because otherwise it would spill everywhere. But you can see the liquid has taken on a new shape. And that's because those molecules are able to move around more easily and slide into the corners or bumps or whatever features its container might have. The other property of liquids is that they have a definite volume. So just like the solids, I don't have to worry about this small container of water becoming much bigger and filling up my room and making me have to swim out of here. And just like solids, these properties are because of the way those molecules move. In liquids, those molecules move around more freely. So what I want you to do now is I want you to think of some examples of different liquids that you know about. I would like you to think about liquids that you might ingest or liquids that you would not want to ingest, maybe something you would find in a garage or utility closet, perhaps liquids that you would find in nature. So I'll give you a moment to think about that. All right, you've had some time to think about some different liquids. Now I want you to think about what is going to happen when we add energy to a liquid. So tell me what's going to happen to that liquid and tell me the name of that process. All right, if you said that that liquid will turn into a gas, you are correct. And if you said that that process is called evaporation, you are also correct. Now, if I took this glass of water and I poured it onto the floor, when I came back in a little while, the puddle would be smaller, and that's because there are some warm heat lamps in here that are helping light the studio. That energy would be added to the water, causing it to evaporate and turn into water vapor. Now, there is a way that we can make water evaporate much more rapidly. So I want you to take a moment to think about how we can make water evaporate very rapidly. For those of you who help out in the kitchen at home, this might have been an easy one. We can boil water. And boiling water requires that we bring it up to a very high temperature. Does anybody know the temperature that water needs to reach to boil? Or in other words, the boiling point of water? All right, at sea level, the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. Now, you might not believe me, but we can boil water at a lower temperature. Some of you might believe me because you may have actually done this before. But I'm wondering if anybody would believe me if I said that you could boil water and keep it at a temperature that is pretty much the same temperature as the water in this bottle right here. Room temperature, around 70 degrees Fahrenheit. I want to show you what happens when we put a bottle of water in a vacuum chamber. Now, a vacuum chamber is simply a container that has been sealed off and has a pump that allows all of the air to be sucked out.
This video is going to demonstrate what happens when water encounters the vacuum of space. So I'm simply going to pour some water from this bottle into this beaker. I'm going to pour off about 100 milliliters. Going to set that there on the vacuum plate. Now notice there is a hole there in the middle of the vacuum plate which is attached to a high strength hose and a high powered vacuum pump just off camera. Now I'm going to place the bottle of water next to it and start the vacuum pump. Keep your eyes on that water inside. Here we go. All right, you definitely saw the water boiling. Notice the water in the bottle did not boil whatsoever. And still a few bubbles going on there. I'm now going to let the air back inside, and it's going to compress any of those remaining air bubbles. So here we go. And not only did it quickly boil that water, but it did so, in fact, without increasing the temperature, because I'm able to easily touch that.
Okay, so something was definitely going on there. And to help us understand what was happening, we need to think about a few things. First of all, I want you to ever think about whether or not you've been in class and you felt like you've had a lot of energy and you just needed to get out and run around. Well, I felt that way in school, and I'm sure you probably have experienced that at some point or know somebody who has. And think about the fact that your teacher does not let you. Your teacher is this exerting force that is not going to let you just run around wherever you want. Now think about that water that I showed you earlier. That hot glass had some molecules that were more brightly colored because they had more energy. Well, if we think about a liquid, we can think about liquids as not just a uniform temperature, but all of these molecules have different amounts of energy. Some of these molecules have more energy than others, and they want to break free and become a gas, but something is holding them back. That something is air pressure. Now, air does not weigh very much. I can lift it all day and I can fill up a balloon with it, and it's not going to give me a really good workout. But air does have mass, and here on Earth it weighs something. So when we think about 62 miles of air above us, which is how much air there is between us here on the surface and the edge of space, air happens to weigh about 15 pounds per square inch. So if you take a circle and put it on your arm, you've got about 1 square inch of your body covered by that circle. So on every square inch of your body, there is 15 pounds of pressure pushing down on it. Your body's actually pushing back to balance that pressure. Well, this water also has 15 pounds of pressure pushing down on it. And when we take that pressure away, there is nothing holding those molecules back, and they're able to break free and become a gas. That's why we see that water boil at a low temperature. It's because there's no pressure holding those molecules back from breaking free. So now we're going to add some energy to our liquid. We can see our temperature has risen, our state of matter has changed into a gas, and our molecules are now flying around much more freely and have lots of space between them. That gives gases 2 special properties. Property number 1 is they take the shape of their container. Now we happen to have built-in gas containers right here in our body, our lungs. So take a deep breath. Now when you breathe in, your lungs are holding that gas, and the gas is taking the shape of the inside of your lungs. There are very tiny air sacs inside your lungs that are getting filled up with the air that you breathe. The air is taking that shape. Now, when you breathe out, something else is happening. Gases are exhibiting their other property, and that is they take up the volume of their container. If we look at these molecules, they're floating around freely, which means when you exhale, those molecules that leave your body are able to spread out. So here's another example of that. When I blow up this balloon, there are these molecules inside. They're bouncing around. They're going as far as they can. The shape of their container, the balloon, is approximately round, but there is a barrier. There's this wall of the balloon that's holding them back. Now, as I let the air out, you can't see it, but you will notice the balloon is getting smaller. I can feel it right here. These molecules, they're moving around in all directions. They're spreading out to take up as much space as they can. And that's because, as I mentioned before, gases will take up the volume of their container. Now, we put some water into a vacuum chamber before, and now we're going to put a balloon inside of a vacuum chamber. So a balloon with just a small amount of gas inside of it, tied off, completely sealed. I want you to think about what is going to happen to a balloon in a vacuum chamber and talk about that. All right, you've had an opportunity to talk about what might happen to a balloon in a vacuum chamber. So let's find out exactly what will happen to a balloon in a vacuum chamber.
To demonstrate the effects of a high vacuum on a balloon. This balloon has no water in it, it's just full of air. It is tied off so no air can get in or get out. We are going to subject this balloon to the vacuum, and without further ado, here we go. So you can see the balloon definitely got bigger, and we think this is probably what might happen to your body somewhat in the vacuum of space. Next, we're going to let the air back inside of the chamber and watch what happens. Here we go. So as we let the air back inside of the chamber, it increased the pressure and the balloon went back to normal.
All right, so the balloon got bigger. It was not getting bigger because there was more air being added to it. The vacuum pump was sucking air out of the chamber. What was happening has to do with air pressure again. The same air pressure that's pushing down on your arm, the same air pressure that was pushing down on that water earlier before, it's also pushing down on the outside of that balloon. And when we remove that air pressure, the molecules inside the balloon, they're able to push out against that balloon wall and stretch it out even more. So what that property demonstrates, again, is that gases will take the volume of their container, and that's because those molecules, they are able to spread out. So I want you to take a moment to think about some different gases that you know of. We've mentioned a few. We've mentioned water vapor, oxygen, and nitrogen. And I want you to see if you can think of any others that you know. All right, you've had an opportunity to talk about some different gases you might know. Maybe somebody said helium, the same stuff that is in those balloons that will float away if you let go of them. You might have also said something like carbon dioxide, carbon monoxide, chlorine can be a gas. So lots of different examples of elements in gas states. Now we've talked about adding energy to all of these different things to change their state of matter. And now I want you to think about what happens when we make something colder, when we take energy away. So think about a gas and think about what happens to it when we cool it down. All right, you might have said it becomes a liquid, and if you did, you are correct. And the process is called condensation. Now, you may have experienced condensation before. If you've ever been outside on a hot summer day with a cold water bottle or a cold glass of juice or something like that, you will have experienced condensation. And it looks something like this. The reason that we get those beads of sweat on the outside of a water bottle has nothing to do with water seeping through that bottle. The reason it does that is because there are water vapor molecules all around us. This room is full of water vapor molecules. And as I walk around with a cold glass of water, my glass bumps into some of those molecules. And when it does that, those molecules cool down and they condense into a liquid. We also see that on blades of grass or plants. We call it dew, but that's the same sort of thing that's happening. Those blades of grass get very cold at night, and the moisture in the air, that water vapor, will condense into a liquid. We can also take it one step further. So what happens when we take energy away from a liquid, or in other words, make it colder? This can be one that sometimes students will overthink. It will turn into a solid, and we call that process freezing. The most common example of that, of course, is ice. But think about this. Lava is a liquid. It comes out of a volcano. When it cools down, it freezes into a solid rock. So freezing doesn't necessarily have to be a very cold temperature. It's just the process of going from a high energy state liquid to a lower energy solid. Now there are some examples where something interesting happens and we can skip over that middle phase and go directly from a solid to a gas. Does anyone know what this is called? This is called sublimation. You may have experienced sublimation if you've ever seen dry ice. Dry ice is solid carbon dioxide. It's 110 degrees below 0 Fahrenheit, and it will go directly from a solid, which you can see here, into a gas. We can also go the other direction. We can go directly from a gas to a solid. Does anyone know what this is called? This is called deposition. We see deposition occurring most frequently during the winter as frost, and that's because when water vapor molecules bump into the cold metal or cold glass, they skip right over the liquid phase, and instead of condensing into a liquid, they deposit into a solid ice. Now, if you were looking closely, you'll notice there is still room at the top of this thermometer for our energy to increase. So what we're going to do is we're going to add a little energy. And when we add our energy, the temperature increases. Our state of matter now changes into a plasma. You'll notice it's glowing. And you'll also notice that the electrons have detached from the protons, and the particles are moving very quickly. This gives plasma two special properties. Plasma will take the shape of its container, and it will also take the volume of its container. So it behaves very much like a gas. However, it is considered electrically conductive, which gases are not. You can almost think of plasmas as like an energized gas. There are a few places that we can see plasma in nature. We can see it in the northern and southern lights, the auroras. We can also see it in lightning strikes. We also have a picture of the space shuttle re-entering Earth's atmosphere, and the energy that a spacecraft entering the atmosphere brings to the gases around it causes that gas to ionize and become a plasma. Those are pretty extreme cases, but you probably have some plasma in your classroom right now. So I want you to look around and figure out where you might have glowing, charged, energetic gas. All right, if you looked up and said the light bulbs, you are correct. Those long tubes of light bulb are actually filled with a gas, and when you turn on the light switch, it energizes those particles inside and they glow. We also see that in neon lights. Neon is a gas that will glow red when it is energized and turned into a plasma. So when you see a neon sign, the only neon signs that are truly neon are glowing red. If they're glowing another color, it's because they're filled with another gas that has been energized. Now, before we move to our final demonstration, there are a few things that I would like to talk about that from time to time can be a little bit confusing. So let's start with smoke and steam. Neither of these things are gases. Most gases, as we've noticed, are invisible. Smoke is made of tiny solid particles floating in the air. They are so small that they're actually able to float. And steam, along with clouds and fog, are tiny liquid droplets or tiny ice droplets that again are so small they are able to float. The other thing that I wanted to mention is gas. We fill up our car with gas all the time, and we've been talking about gases today, but the liquid that we fill up our car with is called gasoline, and we simply call it gas for short. So try to keep that in mind. It can be a little bit confusing, especially since we never actually see what goes into our car. It goes directly from a pump through a hose into the gas tank, and if we don't see it, it's hard to know what's actually going in there. It is a liquid. You can see it here taking the shape of its container in these images. The last thing that we're going to do is take a look at some extreme conditions and see how states of matter behave. So as we're doing this, I want you to think about this phase change diagram where we saw solids melting into liquids, liquids evaporating into gases, gases condensing into liquids, and liquids freezing into solids, as well as solids subliming into gases and gases depositing into solids. So what I want to do is I want to show you a liquid here. Going to give it a little bit of a shake so you can see it is in fact a liquid. And what I'd like you to do is I'd like you to talk amongst yourselves and figure out, what do you think this liquid is? All right, you've had a chance to make a few predictions about what that liquid might be. I'm going to give you a few more pieces of information that are very, very important. So we'll take its temperature. When you look at the readout, take a look at that negative sign. We're looking at negative 103 degrees. And that beeping sound that you heard is actually that thermometer saying this is as low as I can go. If that thermometer could read lower, it would actually be reading 320 degrees below zero. So if you were thinking this was water, it is definitely not water. Water will not be a liquid at 320 degrees below zero. It would be solid ice. So think about this. If we take nitrogen gas, which is the most abundant gas in our atmosphere, cool it down to 320 degrees below zero, it will condense into a very, very cold liquid. So what you were looking at was liquid nitrogen. And what we're going to do is we're going to take a balloon that has been filled with the oxygen and nitrogen that makes up our atmosphere, and we're going to put it into that container. And I want you to think for a moment what is going to happen to that balloon. So talk for a moment and make some predictions about what will happen to that balloon put inside the liquid nitrogen. Okay, now that you've had a few moments to talk about it, let's take a look at what is going to happen.
Grand finale, folks. We're going to take this balloon full of nitrogen and oxygen and dunk it inside of the liquid nitrogen. So here we go. Now the balloon starts to get cold, and the air inside the balloon gets cold too. And those air molecules, they start to slow down. They don't bounce around quite as fast inside the balloon anymore. And the pressure inside the balloon starts to decrease. And it looks like the balloon is starting to deflate. But it's not leaking. That air is condensing into a liquid, a mixture of liquid nitrogen and liquid oxygen. And if that seems strange, it should, because liquid nitrogen and liquid oxygen do not exist naturally on Earth. Just a few more seconds, I'm going to remove the balloon. And I want you to look at the bottom, where you should notice about a tablespoon of liquid nitrogen mixed with liquid oxygen. What you'll also notice is that the balloon starts to go back to normal. That liquid starts to boil. It can't stay liquid here at room temperature, so it starts to go back to a gas, and it reinflates the balloon right in front of our eyes. In fact, in just a few more seconds, it will be nearly completely back to normal. Still a little bit of liquid in there. You might also notice it turning white around the outside and the bottom a bit. That's because it gets so cold, you get some ice which forms on the outside, kind of like why ice would form on the outside of the Saturn V rocket during launch. Just a few more seconds, it's now going to be completely back to normal. And there you have it, folks. A little bit of liquid still inside as that runs around. It now completely reinflates the balloon back to normal.
All right, so in the span of about 1.5 minutes, we saw gases getting so cold they condensed into a liquid. After they were removed from the liquid nitrogen, they warmed up, they evaporated back into a gas. We also saw something interesting. The water vapor in the room, as it bumped into the outside of the balloon, went through deposition and became a solid, that frost on the outside of that balloon. Well, that wraps up our time talking about states of matter, so I want to thank you for joining me today. From all of us at NASA and the Jet Propulsion Laboratory, have a great rest of your day. Bye, everybody.